Welcome, everyone. My name is Felix. I'm a researcher at Cow Protocol, and today I will talk about how you can become a solver for Cow Protocol. My workshop will have roughly 3 parts. First, I will give an overview of what CowSwap is, what Cow Protocol is, what a solver is, and maybe motivate you to become a solver. The second part is about building a solver. So I will try to do some live programming. I hope it works. Where I will basically show you a solver template that takes care of a lot of the boilerplate of building a solver. I will just add a small dummy solver and show you how you can then later use that template as well to build your own solver. And the third part will be about the steps that would follow. So if you have built your own solver, what are the steps to actually participate in the real production competition on Cow Protocol? So how to actually deploy a solver. Let's start with CowSwap. Who of you has used CowSwap before? Who of you knows what the solver competition behind CowSwap is, more or less? Who of you has maybe already tried to implement a solver? Okay, so only people from Cow Protocol, essentially. And okay, and another question. Is someone here in the business of liquidity provision or somehow building a DEX and not necessarily building a solver? Okay, no one. Okay, so then, hopefully you'll all learn in this workshop how to go from knowing about the solver competition to actually maybe implementing a solver yourself. And okay, so you all know CowSwap. So I don't have to talk about that too much. I mean, it's just a UI for swapping currencies. And the UI looks really similar to what the competition does, 1inch or Uniswap. But behind the scenes, there's a lot more going on. So behind the scenes, we are not creating directly a transaction from your swap intent, but we collect intents. So all the people who come to, for example, CowSwap, but also, I mean, maybe use other means of providing us with their intent, we collect it. We create what we call a batch auction from it. So essentially, we create an order book with all the intents. This order book and some additional information is sent to entities we call solvers. Those solvers compete for providing the best execution to our users. And in the end, one of the solvers wins, and that, I mean, the execution they chose is then actually transmitted on chain. So there's a lot of stuff going on. We collect intents, and you probably have heard a lot about intents already at DappCon. I'm not going into detail on that part. Then there's the middle part, where we have an order book, send it to solvers, and they try to find an execution, or try to fulfill those intents. And the second part is what we are going to focus about. So suppose we already have some order book. What does it mean to provide us with a solution? How do we choose the best solution maybe, and how it is then later ending up on chain is not really the focus of the talk. Okay. What do we mean by batch auctions, and what do we mean by a solution to batch auction? And solvers are then those entities who provide solutions. So what do we mean by a batch auction? What you should think of is an order book collecting intents of users who want to swap tokens. But it's, yeah, I mean, it could be just a really simple order book containing only 2 intents to trade, represented by green arrows in this case. One user, for example, wanting to sell DAI and who wants to buy ETH, and another user maybe wants to sell ETH and buy cow tokens. So we collected the intents, the solver gets those intents, this order book, and now what is the solution? And what solvers try to find is counterparties for those intents. So they want to satisfy those intents. And one really simple thing a solver could do is just pick one of those orders, not all of them, just one of them, and try to match it directly using some balancer pool or whatever. So that would be represented in magenta here. One of the user intents, solver decides, okay, that intent I want to satisfy just directly by matching it, for example, using on-chain liquidity, using an AMM, balancer, Uniswap, or whatever, or even private liquidity. This is what happens to some degree with competitors who just look at individual orders and try to match individual orders, maybe using a more complex route, but okay, that's what the competition can do as well. What is special about Cow Protocol is that we have batching, so solvers can provide settlement or can try to satisfy the intents of traders on our platform simultaneously, so multiple intents simultaneously. And one way to also satisfy maybe both of those trading intents is to close this third leg here and create a ring trade. So someone selling ETH for cow, well, let's start here, someone selling DAI for ETH, someone selling ETH for cow, and maybe some AMM selling cow for DAI. That's a way to also satisfy those 2 intents, but it's potentially more efficient because it can satisfy both intents with just one AMM interaction. So this is what some other solver could propose, and the proposals of the solvers can get way more complex. Just one example, instead of settling directly those 2 intents by going from cow to DAI, someone else could propose a more complex routing because maybe the cow USDC pool is deeper than the cow DAI pool, and then swapping those stablecoins might be, frictionless essentially. So some other solver might propose such a route. And what we then do is we collect, after we have sent the solvers some of the order book, they send us their solutions, then we pick the best one, and this gets executed. So we pick the best solution, and the solver who provided the best solution is also rewarded for that. There are some rules around what is actually allowed as a solution, and also, the most obvious would be, users sign an intent to trade, where they essentially say, I want to swap DAI for a WETH, but the exchange rate has to be at least as good as this. So, the execution proposed by solvers has to satisfy that, for example. One additional rule we have that leads to more fair executions and also MEV protection that is not so easily done if you don't have batch auctions, or it's a thing we want to enforce if we have batch auctions, is that there's one price per token. So all users trading on the same token pair, for example, get the same exchange rate, which immediately makes sandwiching attacks within Cow Protocol impossible. And also leads to some other nice properties with regards to MEV protection. And there are some more rules, more subtle rules, which you can find in the documentation. What we what the routing or the matching of the solver sensors has to satisfy to be a valid solution. And then in the end, there's still a problem of choosing the best solution. That's also a bit of a vague concept maybe. And the implementation is a bit subtle, but really think of who provides the best prices, or if multiple orders are involved, it's not just prices, but who provides most surplus. So in the sense of, if you have a lot of sell orders, who can provide more buy tokens compared to the limit exchange rate they specified. And that's collected over all orders, and then who has most total surplus or provides most total surplus to users wins. And okay, that's where the magic lies. Finding routing that actually provides users with most surplus. And then there's sometimes a trade-off between maybe just settling one order can already provide a lot of surplus. Maybe closing the ring trade is more efficient because you only use one AMM and can fill 2 trading intents. Maybe using more complex routing is better, but that might also increase gas costs. So there's also somehow some inefficiencies introduced by more complex routing. And in the end, it's mathematically speaking, a really complex problem. There's no simple algorithm for finding the best execution, and that's why Cow Protocol outsources this, finding a solution to this decentralized solver competition, where every solver can come up with their own algorithm, and in the end, we just compare solutions. So we don't try to find a solution, we just wait for you to send us solutions and choose the best one. Okay, so that's how the general idea behind the solver competition. And now I want to go do some live coding of implementing a really simple solver. And if you want, you can also follow along. So there's a GitHub repo for those interested, where you can scan the QR, or it's Cow Protocol /solver-template-pi. So it's a solver template implemented in Python, where you can, where we'll show you where you have to add some functionality to actually make it a solver. But most of the boilerplate is already there. And okay, so let me go to that GitHub repo and show you how to proceed with building a solver. So this is the GitHub repo, Cow Protocol solver template. Let me maybe make it a bit larger. And okay, so one thing is clone the repo. And after you've done it, you can either run it using Python directly. What I'm going to do is use Docker to run it. So I'm essentially copying that command to build a Docker image of the code that is already in the repo. I can run it like anyone would run a Docker image, and then I will explain where to add some functionality for the actual solve. So let's copy that and add it here. So for me, it's a bit faster because I already built it before. So for you, it might fetch a Python Docker base image, then install some requirements, and then you have a Docker image you can run. And let me run it. Okay, then you can run it like this here. And let me how was it called? It's called test solver image. That's it. Okay. So what this does is it starts an HTTP server on some port, and to that server we can now send order book JSONs, and hopefully by the end of this workshop it will also return something. Okay, let me briefly show you some of the code structure. So to just give you a really rough overview, so this Docker container starts a server which has a few endpoints, so checking for health, getting notified about results of auctions or how the auction we sent was ranked. But what is most important to us at the moment is this solve endpoint. So using that solve endpoint, we can receive a JSON containing the order book and maybe some additional information, some meta information about the state of some Uniswap pools, for example. And then what this does is it parses the request into a batch auction object. And so that's, we won't change that today. And then it potentially solves something. So let's comment that in. And then at the moment it just returns what we call a trivial solution. So it says no orders matched, and that's it. And then it returns that thing. And okay, let's save that and rebuild the Docker container and run it again. So we have this HTTP server which processes a JSON called some solve function. That function at the moment is not doing anything. That's what we're going to fill. And then it creates a JSON file that is returned as a solution of the batch auction problem. So what we're going to do is we're going to fill in some simple method for the solve so that it actually does something with the order book. And then return the solution in the correct format. So, okay, to repeat, what you have to do is look at this solve endpoint, implement something for the solve function, and then convert it to the correct format to the correct solution JSON format. And there are some, I'm going to try to implement a really simple solver now, just a dummy solver. Feed it some test instances and see if the solution that it returns makes sense. Show you how to run a local test environment that already fetches correct, or the actual order books from that are also used in production, feeds it to our solver, and then we can see what it returns locally. That's the goal for this live programming session. So there's already a lot of additional code here. Won't be able to explain all of that, but there are a lot of utility functions you can use to make writing the solver a bit simpler. What I'm going to do now is try to write a really simple solver that just tries to, just goes through the order book, looks if there are two orders in the opposite direction that can be matched directly with each other. And if that's the case, return that as solution, otherwise return nothing. So this self is an order book instance, and okay, has some fields. What we're interested in now is orders. Let's store that in orders. And what we're going to do now is loop through those orders and try to find a match. So for order I in orders, so this is not the most efficient way to do it, but just to to give you an idea of how you can work with orders, how you can try to create a solution. Okay, so we are looping through all pairs of orders, and now we want to try to find a match. For that, we could, for example, use this order I type and maybe explicitly ask, is the byte token of order I equal to the cell token of order J? Is the cell token and vice versa. What we can also do is use, to make it a bit faster, to use some utility functions already contained in the code to see if an order can be matched. So there's a match type functionality that you can apply to two orders. And the result is somehow an enum that tells you, can those orders be matched? Can those orders be matched partially only? So that should be, is it a match as a order match type, hopefully? Oh, let me check. Order match type, and it's both filled. Hopefully. And okay, so just a really simple cow finder. If orders can directly be matched, try to find it. And just for debugging, before we add more code on how to actually construct the solution object, let's just try to run the server with that code and print aloud moo. Let's see. Okay, and now we have a solver that does something. At least prints a moo if there's an order that can be matched, and now we can feed it test instances. And those how to feed test instances is also contained in the GitHub repo. So let's just try that out. Let's rebuild our Docker image and run the server. And now we can look at the GitHub repo, and it contains somehow a command to just curl it some auction instance, also contained in the GitHub repo. So I'm just going to copy that. It's a really small order book instance that is somehow designed to be easy, that contains two orders that can be matched directly, and hopefully, if nothing went wrong, the code will actually produce a moo. It will still return the trivial solution, the empty solution. We didn't change that yet, but it should at least detect that there is a potential cow. Okay, so we have our web server running. We try to feed it order, and there's a wait order match type.
Probably you have to import it.
What?
Maybe you have to import it.
Ah, okay. Order match type. So, I think it's here, order match type. Okay, hopefully that works. Otherwise, yeah, I mean, there's also pull requests on this GitHub repo for two simple one solver that essentially does what I'm doing here, and another one that just tries to match an individual order to a Uniswap pool. But let's go back to the code, and let's try to run it again. Whoop. And now let's feed it the request. What it returns, what we see here, it returns, I mean, I also print the return, so it's a JSON, but it's, contains, it's not an empty JSON, but it contains no orders, no prices, no AMMs, and so on. So it returned the empty solution. And here we should see a moo, okay, because I did this inefficient double loop, it finds a moo twice. So at some point, okay, after the first one, it should just return. So it only finds one moo. Okay, but then, okay, after we found a moo, we can actually construct a solution now that matches those two orders, where we have to specify what are the amounts that are exchanged between the orders, what are the valuations of the different tokens that define exchange rates, and maybe I just copy it from somewhere to make it a bit faster, and I mean go through the code and what it means. So what this does now is, okay, after it has found the cow, uses the execute method of order I and j, and just sets buy amounts and sell amounts to the order, or to the amounts of the matching order. So that has to be done for both orders. So this is one part that is important for the solution solver's return to us, that they specify which orders are executed and what are the amounts that you propose to execute. And the second thing is that you also have to specify prices. That's not so important in the case of just a single cow, because they just trade one-to-one, but if there's a more complex, I mean, maybe a ring trade between users, or more orders being settled, it's important to actually set the correct valuations for the different tokens. And what this code essentially does is, okay, token A is the sell token of the first order, token B is the buy token of the first order, and then you set this, the values for this dictionary self prices for the different tokens, for token A, token B, and set it to, in this case, the sell amounts of the different orders, which, if they are matched one-to-one, define the exchange rate. And that can be coded, or is encoded using prices, for example, like this. Okay, and there's already a return here, so we don't need that. Okay, now we have implemented some logic for, after we found the cow, how exactly which orders are matched and how exactly are the amounts these orders trade. And because we checked that the orders actually can be matched, we know also that limit prices are satisfied. Yeah, so that should result in the end in a valid solution. Yeah, for the solvers you write, you probably have a more complicated logic at that point. And this solve method is where it goes. Next step would be to actually return that solution. So we are still, we are calling the solve function. So yeah, the batch object is updated. There are now prices, there are orders that are executed with certain traded amounts. And now we, maybe rename this to solution. And now we have to fill some of those dictionaries in the JSON with the actual things we want to do. Let me maybe first remove some of the things we don't need for now. Okay, let's keep the AMMs, but we're not using any AMMs. We're just matching two orders directly with each other. And now we have to turn that, the information in the batch object into a valid JSON. And those orders and prices are dictionaries. And let's create those dictionaries. So for order in batch orders, if order punct is executed. So I'm looping through all orders now, and what I'm doing is I'm creating a dictionary that contains order ID as key and contains the order as dictionary as value. I'm not going to go into detail on what the specification of the return format is. You can look it up in our documentation. But yeah, okay. So orders is a dictionary where we have keys, order IDs, and then using this utility function, we can create a dictionary, the correct format from the order object. And for prices, something really similar happens. Due to the values being stored in a slightly different format, it's slightly different. Or let's maybe, so we loop through all prices. Batch prices, which is a dictionary. So we loop through all items in that. So we have the key value pairs. And what we do with them is we take the key and make it a string as key of this price dictionary, and then convert the value to a decimal in string format. So fortunately, the repo already contains lots of functionality around converting to the correct format, so that you don't have to fiddle around with different representations as okay, so I guess I have to import that as well from somewhere. Oh no, I have 4. No, okay. So that should hopefully produce a correct JSON format. So let's rebuild the solver server and try to feed it the instance from before. It should find a cow, should print aloud moo, but also return some actually valid solution that contains those two orders and matches them. Okay, let's see. Let's just send the same small example test instance contained in the repo. Internal server error. Okay. Okay. I actually should have imported that from somewhere. Let's see. So I'm not sure from where. From let's do it like this. Okay, now when I send the order book to the solver, it returns something which looks like this. So it's a JSON containing orders that are contained in the solution, and okay, some meta information on the orders, but also what we call executed amounts, so the actual amounts that you specify as a solver this order to trade. And okay, so we have built a really simple small solver, and one thing. So how much time do we have? Okay, one thing we can now try out is run some of the infrastructure that Cow protocol runs off chain locally to fetch the order book from Cow protocol, send it to our solver, then return a solution to our local version of the order book, and see how this local server responds. And for that, I can let that server run. What we're going to do is what is next in the GitHub repo, connect to the order book. And what I'm going to do is just run a Docker container with exactly this this command here. You can, so let me copy. And okay, there's no env file, so this this Docker container uses as input some environment variables, and at the moment, so let's copy the sample environment variables. So copy .env sample to .env, and let's also have a look at. And okay, let's start the server. It should start now, and let's have a brief look at what the what is contained in this environment variable file. It contains the URL of the local solver I'm running. So it's okay, just local host on port 8000. It contains a URL for an order book. What I'm using here is the order book for the staging environment or test environment on Gnosis chain to make it a bit easier and cheaper to try out stuff. And since it's a test environment, so instead of swap.cow.py, you can submit orders at barn.cow.py, so there's not that much traffic, so you can also submit orders yourself, and there's not so much noise, so you can observe how your solver handles your own orders you submit. And yeah, okay, some other information about nodes, and so the rest is not so important. Okay, we have the server running. We told it to send auction instances to this, to some URL on some port. And what we should see on our solver server that we implemented is that it receives instances of the order book. And so you see, receives an instance every few seconds, but never finds a cow, because at the moment there are, we can look at the order book. The order book on this dev environment on Gnosis chain only contains 4 orders, and none of them can be matched in a cow. And if they could, probably some of the actual solvers in production would match it, so it wouldn't be there for long. But okay, what you see here is that at least our solver receives the order book, sends something in return, and what you also see is, we get those solve post requests, but we also get post notify requests, so responses from the driver component or from the order book component that tells us what happened to our solution in ranking. And because we didn't find a cow, we always get rejected because we only sent the empty solution, which is expected. But now you could, submit orders to the order book via barn.cow.fi, and potentially submit orders in a certain way to actually create a cow, create something that our solver can also find. So in principle, we don't really have the time for that now, but if you now go to this testing environment, barn.cow.fi, so there's really a test environment, but you can actually trade real tokens there on Gnosis chain. And if I just, do some trade weth to GNO, I can confirm the swap. I can sign it. This is not a cow. It's just one order. So to have a cow, you would all maybe have to spam orders on the West GNO pair now. But what you can already see is that hopefully, if you look at this order book component, is that now there are 5 orders in the order book. So before there were 4. Now there's 1 order added, and maybe at some point, okay, the trade happens. So now at some point it should go back to 4 orders in the order book. But that's one way to try out your solver locally, where you already use the real order book, but you don't actually send solutions to us, and what you send is never executed, but just to try out your solver with actual real order books. And Gnosis chain is, there you can also easily submit your own orders and try around or try out some stuff. You could also, if you change this env file, use the order book from mainnet and use some inferior node to fetch blockchain data to let this order book run, and then test your solver with mainnet, within mainnet order book. Okay. So that hopefully helped a bit to give you an idea of how to implement a solver just from the technical side. So start with the order book and start with a template, with a Python template, fill in the, we can switch back to the presentation. So the main things is fill in the solve method with something that you come up with that is potentially more efficient or better than what the competition does, so you can actually win the solver competition. Convert it to the correct solution format, and that's already a good start to get you running. But what are the next steps? What I would recommend is that the next step is to contact the core team. It's not strictly necessary, but for some of the next steps it is. So, I mean, some of the contact information is on cow.fi. A special mention goes towards this solver Telegram group, where some of the production solvers, but also lots of people interested in writing solvers, but also people who maintain or develop DEXs, other DEXs, AMMs, who want solvers to integrate their liquidity. So lots of people in their Telegram channel. You can ask questions if you want. Another good place to go is Discord. So contact the core team. The next thing is also, I mean, probably don't have to tell you, but the next thing would be more testing. One thing is you can actually look at what the competition does. So, I mean, we have an API for various things, but one thing you can do in the API is actually look at solutions sent to us by all the solvers. So if you have a transaction hash of a finalized settlement, you can use our API to get information on the solver competition. And for this particular transaction hash, there's some information on orders and prices and so on, but what's probably interesting to you is that there's an entry for solutions. For this auction, 10 solvers handed in a solution, and so they are ranked by best solution comes last. So then you see which solver actually executed, or which solver had the best execution. You see what call data they actually submitted to chain, and okay, that's public anyways. I mean, it's on the blockchain. But one interesting thing is that you can also look at what the runner-up did and what call data they provided. So you can try to learn from what the competition does, what type of routing they use, or if they specialize on cows, like in my simple solver, or So solvers are free to do what they want, and there you can get an overview of what they do. So that's, okay, for that you don't need to contact us, but one really useful step is what we call shadow competition, where once you have a solver that is somewhat reasonable, you come to us and say, hey, I want to try out my solver. Then you give us a URL of some web server where we can send auction requests, so those solve post requests, using really the production order book. You send us back your solution, it gets ranked compared to all the other solvers participating in the solver competition, and in the end you can see what would have happened. So we don't actually execute anything, so it's relatively risk-free, but that's a really natural next step after you have tested your solver locally. One other thing that at that stage you should look into is what would be summarized as bidding strategies or revert risk. The mechanism we use for rewarding solvers is based on, it's an auction mechanism. And so it's based on how much you are better than the competition. And you can, for example, also say that things like, if you win, you want to get paid at least this much. What is noteworthy is that if you revert, so if you propose a solution, it wins, but for whatever reason it uses so tight slippage tolerances that it can't be executed on chain, you will be penalized. So there's a monetary penalty for not providing a solution that can actually be executed. So at that point, you should be aware of revert risk, use bidding strategies where you say, okay, I hand in my solution that provides lots of surplus, but due to maybe the risk of not executing, I want to get paid at least this much to make up for it if I win. So and at that point it becomes a bit, you have to invest a bit more brain power into how you communicate to us what you want to do with your solution. So it's not just which orders gets matched to what, but also, it's really an auction where you bid for getting the right to execute. Another thing that is noteworthy is that there are some rules. I mean, I mentioned 2 rules, like limit prices of the orders have to be satisfied, so the intent has to be satisfied, and all users have to trade with the same price on the same token pair. There are some rules where we don't know yet how to formalize them into our smart contract, and for some rules we don't even know how to necessarily formalize them even in some off-chain component. So we have some social consensus rules that we don't strictly enforce before you send us your solution, so we don't filter out your solution based on it. But if we see that you are intentionally providing worse prices than you could to our users, then you can get penalized as well. So having a look at some of the soft rules of our competition is something you should do after you've tested the hard rules by submitting solutions and seeing if they get ranked. Okay, that's probably not a lot of news to you that you should do more testing, but what comes after you have tested enough? How to actually deploy your solver in production. What we do is we require a bond from solvers. Why is that? Solvers get access to funds in our settlement contract. So for example, we collect fees in our settlement contract from users to cover execution costs, and potentially a malicious solver could try to steal those fees. So we have a mechanism to prevent that, which is you provide a bond, and if you misbehave, we slash you. It is decentral in the sense that if you actually are able to provide that bond yourself, you can just participate. It's not, no one can, the cow DAO has to allow your solvers into the competition. But, okay, it's a high barrier to entry. 500,000 USC, 1.5 million cow tokens. Most solvers don't do that, or almost all solvers don't do that. What we also have is already existing bonding pools. So one bonding pool maintained by Gnosis and another bonding pool maintained by the cow DAO. And what you can also do is try to make those bonding pools accept your solver or vouch for your solver. But then the bonding pool can decide on additional rules. And what, for example, the cow DAO bonding pool does is, it requires some light KYC because the cow DAO's funds are on the line if solvers misbehave. They also have to show that they provide some value to the competition. So we don't, there's no value necessarily in having lots of solvers who don't do much. So my solver wouldn't be added to any bonding pool because other solvers can do that as well. So what you typically would have to do is tell us that you want to join us. We add you to the shadow competition and see, okay, can you actually win the competition sometimes? You don't have to be super competitive, but you have to show that there is some value in you participating. And then you also, we test you a bit more in this dev environment, for example, before we move you to production. And okay, some other restrictions as well. So I mean, you're rewarded for winning auctions, but if you join this cow DAO bonding pool, some of that reward will be locked for some amount of time. Okay, but that's somehow, yeah. After you set up your solver, after you've tested it enough, again, contact the core team and try to be included in one of the bonding pools. The simplest approach probably is to, yeah, try to be included in the cow DAO bonding pool, and then, yeah, that includes additional restrictions. Okay, just to briefly summarize what I talked about. Okay, I talked about what the solver competition is. So solvers try to match user intents as good as possible. Who matches it best wins. I talked about how you can build your solver starting from a template, and the essential part is you only have to define that solve function. But okay, what you put in there is somehow there's the magic, and yeah, that can give you a competitive advantage. And then I also talked about what the additional steps are to actually deploy your solver in production. And now we have a few minutes for questions. Yeah. And there's a microphone going around.
Do you find that the majority of the solvers that win the competition, is it 1 or 2 or 3 solvers that are just far ahead of the competition, or is it really quite well spread, distributed?
Yeah, good question. At the moment, we have around, let's say, 10 to 15 solvers who participate. I mean, just last week, the solver who won most auctions won about 20%, 25% of auctions. So there are solvers who win significantly more than other solvers, but it's not like 50%. And yeah, the solver who got most rewards in the solver competition, so rewards are based on how much you improve upon the second best, that solver won about 10 to 15% of auctions. So it's not just about who wins most auctions, but also about who can actually provide most utility to users. So the marginal utility you provide upon the second best.
Yeah, you answered the question already.
Okay.
How many bonding pools are there currently?
At the moment, there are 2 bonding pools, one by the cow DAO and one by Gnosis. Yeah, we try to get more solvers to put up a bond, but yeah, it's a large barrier to come up with the funds. But yeah, I mean, some solvers indicated that they would also create new bonding pools, but at the moment there are just 2.
Perfect, thanks.
Hello. I know Yearn made their own solver to make it easier to trade their vault tokens. And so my question was, would that logic be in this solver here or part of the cow swap hooks, or where are those other kind of DeFi interactions happening to help trade these more complex tokens?
I think, I mean, so I'm not sure. Maybe I should refer the question to the backend people, because I mean, Yearn did it before we had hooks, so potentially it's possible to do it differently. I mean, what I showed you is just this: there are orders and you execute orders. What you can also do is we send you some AMMs, and you can say, okay, I'm picking that AMM and I want to trade this much tokens. But there's also a thing that I didn't show, which is called interactions. You add to the settlement, and there you can, yeah, essentially include any call data. So you can also, yeah, use, yeah, other or yeah, call other smart contracts, for example, and do other things besides just transfers of ERC20 tokens. But if you have further questions, there are people in the back who know all about hooks. Any further questions? Yeah, if not, then yeah, thank you for your attention. I hope I could convince you to start searching for better prices as a solver, so our users don't have to. Thanks.